Hi, in this video, we look at transconductance. We are already familiar with transconductance in the BJT. So a quick reminder, we want to build an amplifier from a voltage dependent current source. So if we have some form of voltage V1 which controls this current source, then all we need to do is to put in a resistor here. Then we have an amplifier if V2 ends up being greater than V1. But in BJT, we realize that within a very short window or small window of voltage changes, where the VBE, the V1 is the VBE, so changes which are less than 26 millivolts, so far less than 26 millivolts, so something just below 10 millivolts, we could linearize the function of the BJT this way. So instead of the exponential curve within that short window, we could linearize it as a straight line, and the straight line would have a slope of GM, which is a transconductance. That shows how much the current changes when we change, how much the collector current changes when we change VBE. So similarly, we can do same for the MOS device. So if you have the VGS, we want to know within some small changes in the VGS value. So let's look at the VGS value here. So this is a table of, a graph of VGS or ID against VGS. And this is an exponential curve. So we are looking at the device operating as a current source after saturation. Remember, saturation in MOS is different from saturation in BJT. So after saturation, we have this relation for ID, and we are saying that within a very small window here, we could linearize this function. So what becomes the transconductance? That's what we are looking at. So for small changes, we just differentiate this. So for small changes, ID against small changes, VGS, if I differentiate this, which only works around a small operating point. So assuming this is the operating point, I am biased VGSO. So around this operating point, so around a small operating point, a particular VGS, if I differentiate this with respect to VGS using the chain rule, I'm going to get this expression here. So the 2 will come and multiply this 1/2, and I differentiate what is inside the bracket with respect to VG. So this will go to 0, this will be VG, and multiply that. Sorry, that will be 1. So I'm going to get this expression right here. So that becomes the transconductance of the device. So it means this is the slope when I linearize the function around this operating point. Okay, now we can write the transconductance in other forms. How do we get this form? So what we do is that if we take the ID right here, the original ID after saturation, so let me try and rewrite it as it were, and I multiply the ID by 2, so 2 times ID, which means I'm going to have 2 times this expression, so 1/2 goes out, and I divide this whole expression by VG minus VTH. So the ID multiplied by 2, then I divide this ID by the overdrive voltage, that's VGS minus VTH. Then what I'm going to get is exactly the same as this equation. So I can say another way of writing the transconductance equation is 2ID over VGS minus VTH. Okay, and there is another way, that's the third way of writing the transconductance equation. This time around, if I take the saturation equation for ID, which is 1/2 mu n Cox W/L Vg minus Vth square, and I try making the overdrive voltage the subject, so I would end up getting something like this. I'm going to use this space well. So I end up getting something like the overdrive voltage Vg minus Vth being equal to 2ID all divided by mu n Cox W/L. Okay, and the square root of everything. So what I want to do next is take the expression for transconductance here and replace this side by what I just derived. So that's Vth. So I'm going to put all that in place of the Vg minus Vth. So basically I'm going to get mu n Cox W/L times this. So what I'm going to get would be mu n Cox W/L. Then instead of the overdrive voltage, I put this expression for overdrive voltage, ID over alright. So if I decide to put this back inside the square root, then it's going to look like this. Square. So all this term here would cancel one of that, and I can say Gm is equal to 2ID and this gives us a lot of information about the Gm. So it tells us that if ID remains constant here, then Gm is directly proportional to root like that. So we can derive other expressions or other relations from them. Okay, so if we have ID also constant, then Gm from this equation tells us proportional to 1 over Vgs minus Vth. So based on this, we could get an amplifier just as we did for the BJT. Okay, so I hope you enjoyed the video. On the next video, we are going to try one worked example. Bye.